Hi guys, this is the third deliverable for the team Bit Bandits. This team is consisted of Rachel Verestigi, Alexis Rogers, Brandon Navarrete, and Payne Five. So we find that there was a high cost and inefficient use of traditional solar panels. We are introducing an automated technology to substantially reduce these barriers, enabling a more effective process of solar energy harvesting. We found that solar energy was not being fully utilized due to its inefficiencies and logistical challenges. The current solar energy market relies heavily on fixed position panels, leading to suboptimal performance. Some of our direct customers would be residential owners, commercial solar farmers, utility companies, and military exercises. Our indirect customers would be people such as investors in the renewable energy, policymakers, and environmental agencies. Here are some of the design requirements going into creating the system. We wanted to ensure high efficient energy collection, autonomous operation, scalability, adaptability to perform in any and multiple different terrains, high energy storage, as well as being safe and compliant with all laws and regulations. Here you can see our individual bots. You can see the robot name, the role, the functionality, and the assigned member who created and also will speak for their bot.
Hello everyone, my name is Alexis Rogers and I've created the ScoutBot. ScoutBot is created of a couple different components. We have an Arduino board inside the body of the ScoutBot, 4 high traction wheels with DC motors, 2 light sensitivity sensors, an RFID system, and a solar panel to support self-sufficiency. Here are a couple other views of the ScoutBot where we can see the solar panel's use, our light sensitivities on 360-degree swivels to be able to surround all different types of areas, and our tracking system with all of our wheels. So that way we can go through any different type of environment. We have our electrical circuit here consisting of an Arduino board, 2 DC motors, 2 potentiometers that represent light sensitivity sensors, and our servo setup. Our basic flowchart for the ScoutBot is initializing components. Once they're initialized, they will then read the light sensitivity values. It will then determine is the left sensor reading higher? If no, it will then identify if the right sensor is reading higher. If either are then reading higher, the ScoutBot will then turn in that direction and then move forward and continuously going through this loop until it is at the area with the most optimal light. Here are some snips of the code. I'll go through a little bit here in Tinkercad. So here we have our code. And so these light sensors will get and absorb sunlight. They will then output a value for how much sunlight they're getting in. And then there will be a differential equation that will then identify what light sensor has more sunlight coming in, and it will then send that information to the servo, and the servo will then start moving and pass on along the information to the DC motors that will then tell the wheels what direction to turn into. And as you can see, the code started and the simulation is running, so it's working. And as we increase the value of the sunlight and how much these meters can take in, the servo meter will move around and send signals to the DC motors, turning the wheels. All right, thank you.
Hi, my name is Rachel Verestigi, and I will be presenting my PathBot for our Team Project Deliverable 3. The PathBot ensures safe and efficient navigation pathways for the swarm, and this requires the robot to have an assortment of object detection sensors, which is why I decided to go with the 3 ultrasonic sensors on the left, right, and front of my robot. I also equipped it with a LiDAR sensor for the front of the chart. For the front, to chart efficient paths for the other bots by transmitting lasers that bounce back to the sensor to produce 3D maps for the robot. The base of the bot houses an Arduino board and battery that powers the bot. The entire bot is comprised of strong aluminum chassis to make it durable. The robot also has an antenna on the top of it for Wi-Fi connection to receive the latest weather reports and to ensure quick communication with the rest of the swarm. So if there's ever a change in like the route or inclement weather is coming, the PathBot is designed to quickly communicate with the rest of the swarms so they can all adjust accordingly. This is my flowchart. The PathBot will read the input from its sensors and determine how it should move based on these readings. If it is clear on the right, it will move right. If not, it will try to look for an opening on any of the other sensors. And if not one of them is cleared from obstacles, then it will reverse briefly until it can find an opening and then reread the sensors. This is my electrical circuit for my bot. The Arduino board and the 9-volt battery supply power for the robot, and there are 2 DC motors for the front 2 wheels of the bot. The third back wheel is more just for stability. And there are 3 ultrasonic sensors, as said before, on the left, right, and front of the robot for object detection. And the breadboard is for circuitry. And this is my Arduino code for my PathBot. I was able to print the results so I can see how close things are from the PathBot and used if-else statements to detect when each sensor goes off and what to do next when a sensor does go off, and to move backward when no sensor is cleared, and then reread each sensor again. And that is my PathBot. Thank you.
This is Payne Fife, and I'm going to be discussing my Harvest Bot for our Team Project Deliverable 3. The Harvest Bot picks up signal from the PathBot and the Scout Bot on determining the best location to harvest the most amount of energy. The Harvest Bot is built up of 4 solar panels, 4 all-terrain tires, 3 ultrasonic sensors, energy transfer couplers, a junction box, and built around a full battery. The Harvest Bot is built up of an Arduino board that's in the junction box, a rigid aluminum chassis that is fitted around the battery pack, a battery, individually operated DC motors with all-terrain tires, 3 ultrasonic sensors, and an energy transfer couplers to transport energy to the transport bot. The components list is listed here. They've all been covered. This is just different looks at the actual bot. The electrical side of the Harvest Bot shows that the 3 ultrasonic sensors are wired into the Arduino board, and the 4 DC motors are wired in as well with a 9-volt power supply. The electrical code for the Arduino board is listed as shown. We determine the trigger pins. We go through, we validate that which sensor, either front, left, and right, are detecting a obstacle to avoid. And if there is no way around, the bot will then reverse. This is the Harvest Bot's flow chart. When it picks up a signal from the PathBot and the Scout Bot, it will start to travel to that location. Front sensor detects an obstacle, or the left sensor, and then the right, and then it will travel on. So we got front, drives forward, left, turns left, right, turns right. As for the Tinkercad model, I'll pull this up now. We can see here that we start the simulation as shown. We have no motor turn since we have a obstacle detected in each direction. Once our direction for the ultrasonic sensor for that determined side loses or picks up an obstacle, it will then advert to the DC motors powered by the Arduino board and determine which way to travel to. That's all.
Hi guys, my name is Brandon Navarrete, and I'm here to introduce the Transport Bot. This bot has an Arduino board that's enclosed in a rectangular housing unit. This unit sits on a chassis that was designed to be low center of gravity as well as be optimal for sharp terrain. We have 4 DC motors as well as 4 tires. We also have 3 ultrasonic sensors that provide obstacle detection for the front, left, and right of the vehicle. We also have 3 solar panels on top of the vehicle that aren't necessarily for solar harvesting rather than self-sustainment. Here we have a zoomed in look at the mechanical features. We can see how the DC motors connect to the tires, as well as how the frame took shape. Here we get a better look at the electrical circuit. We have the 9-volt power supply, as well as the 5-volt output from the Arduino board. The DC motors are controlled by the motor drivers. And these drivers are connected to the PWM pins for input-output operations. We have the ultrasonic sensors that are powered by the Arduino board, and they're connected to the analog in for their operations. The sensors provide data that determine the high and low state, and these high and low states provide the ability for the DC motors to operate and maneuver the vehicle. Here, we have a flowchart logic that shows how our vehicle operates. You can see that we immediately start to detect obstacles in the front of the vehicle. If there's no obstacle and the path is free, we'll drive forward. If not, we'll look left and we'll always search in this counterclockwise rhythm. And if we can't turn left, we'll look right. And if we're blocked in all 3 directions, we will reverse for a fixed amount of time to provide us an obstacle-free path. Here's some code that shows the structure of how the vehicle operates. You can see the variables that define, as well as some of the functions that are implemented. We'll go more into this in the simulation. So here you can see how the vehicle or the circuit board takes shape. You can see that the simulation is running and that we immediately get some kind of input. Let's figure out why. You can see that the left and the front are blocked, so we're slowly reversing while turning right to look for a new path. If we simulate no objects in front of the vehicle, we'll continue to drive forward. And you can see that the motors directly reflect the actions or the data from the sensors. So here we have the collective swarm behavior. We have an initial start input, which sends the scoutbot for its operations. It begins this loop of looking for maximum sunlight, and if it can't detect it at a given point, we assume that the end of the day has occurred or some other issue. So then we report to the hub. If maximum sunlight is detected, we send the pathbot out to map and report an appropriate route. The harvest bot then follows these directions and begins the harvest. And then the harvest becomes its loop, checking to see if it's collected enough energy to call the transport bot. If we never reach full max and then time is after 6 p.m., we end the day and then we report to the hub. If we do have a max capacity, we call for the transport bot to collect energy and send it back to the terminal or to the base. Given our research in material and labor costs, we find that it might be around $200,000 to $320,000 to fully market and fund this project. Including the value of reduced labor needs and energy cost reduction, we find that the system valuation may be appropriate around $800,000. Each unit may be around $65,000 to produce, plus or minus 15%. We use reports from BattleBots where they reported $100 per pound up to 25,000, and these are non-autonomous vehicles. We also looked at agriculture bots, which are very similar, but slightly different in their operations. A small vehicle in this field may be around $250,000 alone. We did a fair bit of research into competitors and similar market presence. For example, these 3 competitors right here. Although they are very similar to what we are doing, they are not similar in the functions. Our bots are designed to feed solar energy back into the grid rather than using it directly for their own task. Our system design is not a replacement of another product or an imitation. We are a different flavor in the world of solar energy. Investing in our system can reduce energy bills over time, almost in the sense of a return on investment. With all this mentioned, the overall system price comes in very competitively in the market for considering the potential return on your investment. Our team has learned the benefits of iterative prototyping, refining functionalities, and defining a clear project scope. Learning to market our designs has taught us to value the understanding of customer needs, staying adaptable, and learning from those who've paved the way if such an individual exists. Between management and teamwork, our team has discovered that clear communication within the team were essential. We made sure to leverage each individual's strength, which helped us ensure the project's success. Here's what we would have done differently as individuals for this project. Solar harvesting employs swarm robots with specialized functions to address efficiency, autonomy, and scalability within the solar energy field. While drawing on existing knowledge, our project pioneers new methods for reliable and versatile energy collection. Our innovative approach aims to redefine solar energy through using advanced robotics and engineering. Here are our references. And thank you for your time.